Hello, it's Keith here, and this is lesson 2 of my PowerPC assembly programming tutorials. Now, we looked at some very beginning basics last time, some simple things like labels and a few addition and loading register commands. We're going to go into the addressing modes in quite some detail this time. The addressing modes are the way that we work with data, the way we read data from memory addresses and things like that. We're going to go through all of them. We're going to see a simple example of every addressing mode so that we know them all in entirety. What we're also going to do is we're going to look at the stack. The stack is a fundamental part of the PowerPC and most of the processors. It's the way that we back up and restore variables over short periods of time when we don't want to store them to a specific memory address, and having them in the registers is no longer convenient, like we're calling a subroutine and we need those registers for other purposes. So that's what we're going to be looking at today. All of today's example code is available on my website. We're going to be looking at lesson2.asm today, and as always you can go to my website, download the source codes and build scripts. The idea is you compile this yourself and try things out. Anyway, let's go over to our source code and let's take a look at today's lesson. Okay, so here it is. At the start, we've got these set of jumps here to the various sections. The first one we're going to look at is this top one, addressing mode. So let's disable that stack and subspecial then. Let's run today's example on the GameCube emulator. Okay, and let's see what we've got. Okay, so at the start of our code here, we've got a label addressing mode, and we are loading some immediates. We're loading some 0 values into registers 3, 4, and 5 here. And this is just so that we've got a clear starting point, because some of these may load in 16-bit values and things, and so we want to know the starting point we've got. Now, the first addressing mode we're going to look at is signed immediate, and if you look at the official documentation, you might see this referred to as SIMM in the example commands and things. So this is where we are loading an immediate 16-bit value, and that value is a signed number. So this means it can go from -32768 to +32767. Why that range? Well, that's just the way the immediate values work. So that's what we've got here. Now here we are adding the signed immediate -1 to R3. -1 is the right-hand parameter, the middle parameter is R3, so those two are being added together. The destination is always on the left in these commands, so the R3 on the left of the two commas here is the destination. So this is saying R3 equals R3 plus -1, if you will. It's an add command, but we're adding a signed immediate of -1. And you can see here that R3 has become a large number of Fs here, and that is because that is the hexadecimal representation of -1. Now, if we change that to -2 and we run again, well, you will see now that hasn't changed to Fe. F would be -1, Fe is -2 there. Lots of Fs there, though. All of the top bits will be inverted there with the negative numbers, so that's why we've got all of those Fs there. Anyway, so that's our negative numbers. As I say, these are 16-bit immediates, so if we do 32768 here and run again, that will run just fine. That is -32768 there. But if we try and do +32768, our assembly didn't work there, and we will see we get an error here. Out of range, we're being warned that that is not within the valid range for a 16-bit signed number. So our signed numbers do have some limits. And as I said last time, if we want to work with very large numbers, we need to combine two commands together. In this case, if we wanted to do an additional subtraction, we might need to load one of our registers from a memory address containing the very large number we wanted to add or subtract, and then add or subtract that register from another register. So there's always ways to work around it, and you'll come to understand those later on, so don't worry about it too much. So that's signed numbers, and the vast majority of immediate commands work with signed numbers, and there's only really one category of command on the PowerPC that doesn't work with signed numbers, and that is logical operations. We're going to cover logical operations later on, so don't worry about it if you don't know what they are. But these are things like AND or XOR NOT, things you might be familiar with if you've ever done any courses on programming, or if you've ever looked at electronics and things. But as I say, we'll cover them later, so don't worry about them too much. But in a lot of ways, signed numbers don't necessarily make any sense for logical operations, because they tend to be thought of as working at the bit level, and so on the PowerPC, all of these work with unsigned numbers. And so these are all treated as unsigned, and they will have the sort of reference as UIMM in the official documentation. So here we've got the value FFFF as the parameter here, and this OR command we'll basically just set those bits. We loaded R4 with 0 here. We are ORing in this value here, and that gives the result of 0, 0, 0, 0, F, 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 F. So it's just set the bottom bits of the R4 register effectively. And we saw last time that we can use a load immediate shift command, LIS, and also an ORI command to combine two numbers together to load a full 32-bit value into 16-bit parts. Again, not really part of what we're covering today, but just referring back to it there. So that is signed immediates and unsigned immediates, but of course we work with things other than immediate values as our sources. We will just work with registers, and we've done this as well. So here we are basically loading the destination R5 on the left there with R5 in the middle there plus R4 on the right there. So R5 and R4 are our source registers, and R5 is our destination register. So this is referred to as register addressing, where all of our parameters are registers. So that's another option that we can do. Now, those are the sort of ways of working with values either from immediates or the registers that contain values already. But in a lot of cases, we're going to want to work with values that are somewhere else in memory. And so we've got a block of data here marked by .data there that puts it into the data segment. Once we've created a data segment, we need to go back to a text segment. Rather confusingly, a text segment actually means program code. Data segments are a binary data that our program may use, but the text segment is actually the program code, which of course here is literally assembly source code, which is text, but it will actually be binary data once it's been assembled. Anyway, we are defining some 32-bit values here, and the assembler I'm using refers to these as long, so that is a 32-bit value. And this is another very convenient way, and arguably the most convenient way, of working with full 32-bit values rather than using LIS and ORI or ADDI to combine two 16-bit values together. So here's our sample data here. And what we're basically going to do is we're going to load in from that sample data, and we're going to use something known as register indirect with immediate offset. Well, that's a little bit complicated. What does that mean? Well, we're going to load the address of the sample data into R3 here, and we're doing it in two parts. We're using load immediate shifted to load the top 16 bits of sample data. At HA, we'll load the top half of the sample data address there. That should actually be at H, not at HA. I've made a mistake there. HA would be if we were using ADDI. It probably worked in this case because the address is quite low anyway, but it should have been at H there. And so we are loading the top 16 bits of the address sample data into R3, and then we're ORing in the bottom 16 bits. At H is at high, and at L is the low part. And so we're splitting sample data into two parts, a high part and a low part, and we're loading the high part into R3, and then we're ORing in the low part into R3 there. The end result of those two commands is that R3 contains the address of sample data. What are we going to do with that? Well, we're going to use the address in R3 as our source for the next command. We're going to load a byte, and then we're going to fill all the other used bytes, because there's 4 bytes in a register, so we've got 3 unused bytes there, and we're going to fill those with 0. So we're loading 1 byte and filling 3 bytes with 0, LBZ, load byte and 0, extend, and we're going to load from the address in R3, but we're going to specify an immediate offset of 1 byte. So that one outside of the brackets is an immediate offset of 1 byte. And the R3 in brackets specifies the indirect address in R3. So this is effectively saying load R5 from the address in R3 plus 1. And that is adding 1 to the address in R3, not adding 1 to the data loaded from the address in R3. Okay, so well, let's see what actually happens when we run this then, and let's see if we can make sense of this. Okay, so we have got our memory address here, 8001,000 here, and that is the test data here. You can see some test data there, and if we look at our code, you will see it's the same data as we loaded here. So that is our test data, and that's what we have loaded into R3. You can see R3 contains 8001,000, and that's the address that we're showing here. That's our sample data. And then what we have done is we've said load R4 as a byte and 0 extend. And so what does R4 contain? Well, R4 contains DC. Now, where is DC? Well, it's at memory address. It's at 1 byte offset from that base memory address. The base memory address is in register R3, and we have loaded in from an offset of 1 because we specified an offset of 1 just here. Now if we close our example here and we set an offset of 2, for example, and we compile again, assemble again there, well, we've now loaded from an offset of 2. So now R5 contains the value BA. And that is because here is offset 0, FE, offset 1 is DC, offset 2 is BA. Now, in a lot of cases, we would actually probably want no offset at all, and we would just specify a 0 in that case. And that is going to run just as fast as having an offset. So that is how we will load in from the register R3 on its own with no offset. We would actually specify an offset of 0, and you can see if we just assemble that again, you can see we've now loaded in R4 from the memory address FE here, which is the original base address in the R3 register here. So we've loaded that from there. So that is how we can use an immediate offset to an address in a register there. So register indirect with immediate offset. But there will be cases where we want to actually not use an immediate offset. We may want to use an offset in another register. And this comes into something that's very important and a little bit unfortunately confusing about the PowerPC syntax. Now, I've updated my cheat sheet, rather embarrassingly last time I'd forgotten to update it. And so we now have the new R0 equals 0 column here, which I tried to show you last time. This denotes which of the commands treat the R0 register as a hardwired 0. So you can see if there's a Y there, those commands will have the register as a hardwired 0. But that's not actually what I wanted to show you this time. What I wanted to show you this time is the rather complex range of commands that some of these operations have. So for example, the load byte and 0 LBZ command here actually has various other options like LBZX, LBZU, LBZ UX, and you can see that a wide range of these commands have all of these other options, and unfortunately the options actually vary depending on the type of command that they are. And so what I've tried to do here is put a summary of what the other options are here in the top here, just to try and explain it. And when you start to work with the PowerPC, you will start to understand what the options are and why they exist for certain commands and not others. In these tutorials, what we're going to do is generally we're only going to use the most basic versions of the command, and what you'll need to do is you'll need to either check the cheat sheet or check the official documentation to understand what the other options that are available to you are when it comes to these other sub-options that we're going to try out now. Alternatively, the simplest way to test them is actually just to try and assemble it. If the command you're trying to specify doesn't exist, it simply won't work. Now, the one we're going to try this time is the suffix X. So we're going to use the LBZ command, but this time we're going to put an X on the end. Now, what does this X do? Well, this means rather than use an immediate offset with our register indirect, the X suffix specifies that the offset will be specified by a second register. And so here we're specifying two registers here, R3 and R6. And what this effectively means is that the register R5 will be loaded from the address in R3 plus the registers R6. And so this becomes the equivalent of this command here rather than this command here. So again, we've got our base and we've got our offset, but our offset is this time in another register. And so if we run this again and we see the result, well, you can see here that R5 has been loaded with BA. Why has R5 been loaded with BA? Because R6 contained 2, R3 contained our address to the sample data. The sample data is here. You can see the same address as before. And offset 2 contains the value BA. And so that's why that has been loaded into R5 there. So that time our offset was specified in another register. And why you will want to do these two options will depend on your code. Often in your code you might have various offsets to a base address that have different purposes. If you've got a game, a certain offset of 4 might be the X position, an offset of 8 might be the Y position, an offset of 12 might be the player's lives, that kind of thing. And so you point the base register to the start of that data, and you use the various offsets in your code when you want the various parameters. This is also often used with hardware. If you're using a piece of graphics hardware, you point to the base address of the hardware's registers and use the offsets to set the various parameters of that hardware. So that's why you may want to use an immediate value. You may want to use an offset though if you're sort of streaming in data from a source. For example, maybe you're transferring bitmap data or something, so you point the your R3 in this case to the start of the bitmap data, and then you would change R6 as you're reading in the various lines of your font or whatever. So as I say, there are going to be cases where using a register pair may be more appropriate. There'll be cases when you would prefer to use an immediate, and as I say, you have both options. The important thing is the suffix X in this case specifies that we are using a register offset rather than the sort of default of the immediate offset. Okay, so that's what the X option does. Now, what about the other options? Well, the other option we have is the U suffix, and we can use this with an immediate value or with the X option for a pair of registers. The U means update, and what this does is it updates the base register by adding the value of the offset that we specified. So this would be known as auto-increment on other systems. So if we just run this example here and we see what happens, okay, so we've got R3 containing the pointer to our sample data. We've got R6 containing the value of 2. We're using LBZU here first with an offset of 1, and then we're using LBZUX with our R6 offset, which is an offset of 2, and let's see what happened. Well, we're using the monitor to dump the results each time. So the first time here, before we've done any loading, R3 points to the very start of our test data here. So you can see that in R3 here. We then loaded in our single byte here from an offset of 1 here. The offset was specified as 1, and R3 was specified as the register of base, and we've used the U update option here. So R3 was incremented by 1, it's gone up by 1 there, and you can see DC has been loaded into R4 because that is at position offset 1 there. So the update as R3 has occurred after the load was done, and so that's what's happened there. Now what we've done next is we've used R6 as the offset this time with the X option as well as the U option, and we are loading into R5 from R3 plus R6 effectively. So here is R5. R5 has been loaded with the value 98. That is offset by another 2 from the last position of R3. R3 used to point to the DC entry, and now it's been offset by 2 and points to the 98 entry. And you can see that R3 has gone up by another 2, and R5 has been loaded with the value we specified there. So that is the effect of the U option. It updates the base register there, R3. You can see it's changed each time. And the X option specifies not to use an immediate value, but to use a register offset there. So that's what those commands do. Okay, so those are examples of U and X when used with loading commands. In this case, the option is load byte and 0, but there are a variety of other load options which we will look at later on. Now, that's one suffix we can use, but there is another suffix that's very important, and this is the full stop suffix. What this means is it will update the condition register. What's the condition register? This is the flags register on a lot of other systems. And so this is the register that keeps track of the result of the last register and is used for things like comparisons and used for branching and things like that. So it's something we may want to update sometimes, but other times we may not care about the results of our last command, and so we may not want to update it because we may want to keep the previous update from a more important command that will cause a branch later on. So what we can do here is we can put a full stop at the end of a command, and that will cause that command to update the flags. Now what we're going to do here is we've got a simple loop here. We're loading R0 with the value of 6 here. MTCTR, bit of a complex command that's kind of outside of the range of what we would really want to cover today, but this is moving it to the count register. And what we're going to do is we're going to loop using BDNZ, and we're going to run this sequence 6 times. It says count 4 here, so obviously I changed my mind in between programming this. So what we're going to do is we're going to run this add command with an update of the condition register each time. And we're going to see what happens when we repeatedly add 1 to this very high value here, or very low value, just depending on whether you consider it a signed number or not. Okay, so here you can see our registers here. You can see R3 contains this very high number here, and we're repeatedly adding 1 to it, and then you can see it rolls round to 0. Now the important thing you should be looking at here is the very top nibble here. You see this 8 at the start of the CR register here? Well, you can see that changes to a 2 and then a 4 here. And why has that value changed? Well, it's simply down to the value here in the R3. You can see when it rolled back to 0, you can see that the value in that changed to 2, and then when it became a very low number, you can see it changed to 4, whereas before it contained a value of 8. And this is to do with whether R3 could be considered a negative number, whether it could be considered a positive number, or whether it's simply 0. Now, it's beyond the scope of what we're looking at the moment, what the bits in CR do and how we can actually use them. But the important point I'm making here is that the CR register was altered by this command here because it had that full stop there. Now, if I take away the full stop here and I run this again, we will see that actually that has now changed. And you can see in all of the cases now, the top nibble of CR contains the value of 8, irrespective of what the previous calculation did, because the full stop defines that the condition register should be updated. If we take it away, the condition register simply is not updated. So that's the effect of that there. Okay, so those are the addressing modes that we're going to look at here. Now what we're going to do next is we're really going to sort of dive into the load and store options and see what real options we've got. We only very briefly touched on it, and we only used the loading of bytes and zeroing. That's kind of the most simple, and it was in a lot of ways the most practical for seeing how the bytes were being loaded in. But what we're going to do now is we're going to look in more detail at some of the other options. Okay, so what we've got here is another block of sample data here. We have got this being shown to the screen here just so for convenience. And what we are doing here is we are loading the address of sample data in 2 parts into R8. We're using LIS and ADDI this time because we're using ADDI. We need to use @HA to get the high part here. High adjusted for addition here. That's what HA stands for. And so R8 will contain the address of sample data after those 2 commands. And we're going to use R8 for a variety of tests here. We're going to load a byte and 0 extend here. A byte is 8 bits. We're going to load a half of a 32-bit value, that means. So that's 16 bits. And we're also going to 0 that. And then we're going to load a word. And on this system, the PowerPC, a word is 32 bits, so 1 full register. So that's what we're doing here. And we're loading these from R8. And the word we're going to offset by 1 byte there. Okay, well, let's see what's actually happened. Okay, so we loaded R3 as a byte and 0 extended. So the bottom byte of R3 contains FE. All the other bits contain 0 there. Okay, we then loaded a word into R4. And so we can see FEDC. And the reason we can see FEDC is because that is offset 0 from the address there. The address, of course, being loaded into R8. You can see the address being loaded there into R8, 800-10018. And you can see that address there. And both of those were offset 0. And then we loaded R5 from offset 1. So let's see R5, where you can see DC BA9812. And FE is at offset 0. And you can see at offset 1 DCBA9812. Why did we offset by 1 byte there? Well, it was to make a point that this command can do that. On some systems, you would need to be 32-bit or 16-bit aligned to correctly load a 32-bit value. But the PowerPC is able to actually load at an offset of 1 here. That will work just fine. So we're just showing that off there and that we are able to do that. Now, in all of these have been 0 extended, which means that any unloaded bits will have the value of 0. You can see there, all those contain the value of 0. There is an alternate option, which is LHA. This means load half for algebra. Now, some systems would think of that as arithmetic, and actually it's the same thing. What it means is we are sign extending the value. In practical terms, what happens is the top bit of the value that we loaded is used to fill all of the unloaded bits. So in the case of us loading the value FEDC, the nibble F contains a top bit of 1. So all of the unloaded bits are all filled with 1s, which gives the top half FFFFF there. So that has been loaded in there. R6 has been loaded with for algebra there. And that is why that is the LHA command there. R7 has been loaded for algebra as well with an offset of 4. Now an offset of 4 means we have loaded in the value 1, 2, 3, 4. Now in that case, the top bits are all 0, and so that kind of looks like the 0 extend option, but it's not the 0 extend option, because if we'd have loaded in for an offset of 0, it would have filled all the bits with 1. It's simply that the nibble that contains the number 1 there in the 1, 2, 3, 4 has a top bit of 0, and so that top bit has been filled to the rest of the values. Whereas you can see here when R4 is loaded with FEDC by the load half and 0 command, the extra bits were 0, but when it was loaded into R6 with the LHA command, the extra bits were filled with the top bit and they were all filled with F. This is all to do with signed numbers. If you're loading in a signed number, you need all of the unloaded bits to be filled in with the top bit. It's a bit confusing and you may not understand it at the moment. As I said before, I've got a tutorial on hexadecimal numbers with regards to signs. I did it on the Z80, but it entirely applies here as well. So please check that tutorial out. If you search my YouTube channel, you will find that. Now, that is loading halves for algebra. Now, there are two sort of limitations of what we've got here. Now, basically, we do not have a load byte for algebra command. That does not exist. What we do have is an extend signed byte command, which will, as a second command, fill in the extra bits. The other thing we don't have is we don't have a load word for algebra. The simple reason is we don't need one. When we're loading a 32-bit value, there are no bits that aren't being loaded, and so if a number's signed or unsigned, it's entirely been loaded anyway. It's the halves, the 16-bit values, they've clearly felt are important to sign extend, so they've provided a loading command that will do that for you. The bytes they obviously thought was less important, less likely to be loaded, and so you will need to use an extra command, extsb, to extend the sign of a loaded byte. And as I say, we will look at that in a later example. So that is how we can load in our bytes and our halves and sign extend them as required. Okay, so that's how we can load in from addresses on the PowerPC. Now, one command we're going to look at this point is the LA command, and this actually stands for load address. And this, it's kind of a little bit misleading. What you might imagine that it's going to load an address in the way that these have loaded in the address sample data into a register, but that's not actually what they do. What they actually do is calculate the effective address of a previous command. So, for example, load address R3, 4, R5 here is actually going to take the value in R5 and it's going to add 4 to it. And so if you have a look here, you will see R5 here contains the value 8001018 here. And so what we are effectively going to do is we're going to add 4 to that and store the result in R3, and you can see R3 contains that value there with 1C at the end. And if you know your hexadecimal, you'll know if you add 4 to 18, you will end up with the value 1C. We've then also added 16 to the value in R5 and stored the result in R4 here. And you can see that 18 there has become 28 there. Now, why would you want to do this? Well, there may be cases where you need to calculate an effective address and then use that in other places in your code in a single register without re-specifying the offset multiple times. And this is how you can do this. And this is effectively an add-I command in a lot of ways. So this is another pseudo operation being done by the assembler. But I thought it was a good point to discuss it here, because you will see this load address command and you might think it's doing something cleverer than it actually is. So there we go. We've learned in how we can load in bytes from addresses in registers. What about storing them? Well, in the same way as we have load byte, load half, and load word, we have store byte, store half, and store word. Now, these are a little bit backwards compared to the other commands. Usually the destination is on the left and the source is on the right. With the store byte commands, the source register is on the left and the destination is on the right. So R3 is the value we're storing, and R5 offset by 8, offset by 12, and offset by 17 here are the destination of that command. And this does make sense if you think about the fact that the store command is doing kind of the reverse of what the other commands do in a lot of ways. The register is the source and the memory address is the destination, whereas in the other cases it's the other way around. So it does sort of make sense, but it's a little bit confusing the first time you see it maybe. Anyway, so what we've done here is we have got this value in R3 here. We've loaded in the value basically FEDCBA98, and we are going to store that in various ways to various addresses. So firstly, we've stored the byte to an offset of 8. So this will store only basically the lowest part of this register, because the byte part is the 98 part there, if we're only storing 8 bits. And you can see that has been stored there, 98, and that is an offset of 8 from this address here, which was loaded into R5. You can see that address is loaded into R5 there. So that's when we stored a byte. We're going to then store a half, and we're going to store that as an offset of 12 here. Well, you can see we've got the value BA98 there, and you can see that is the bottom half of the register there. So we've stored the bottom half of R3 there. Now, it's important to notice that in memory it is BA98. That is because the PowerPC on this system is a big endian processor. A little endian processor would actually reverse those and store the 98, the little part, first, and then the BA part, the big part, second. But this is in big endian mode, so BA and then 98 in memory. Now, the important thing to understand is that while the GameCube uses the PowerPC as a big endian system, the PowerPC is actually capable of working in either mode, so you just need to check the hardware you're using if you're not using the GameCube and see whether it is actually running the PowerPC as a little endian system or not. So just something to bear in mind that you know, while in a lot of cases the PowerPC may be big endian, it is not as a rule a big endian system. It can be either. So there we've stored a byte, we've stored a half, and then the final thing we've done here is we've stored a word to an offset of 17. And you can see there we have stored the entire register. And once again, we've used an offset of 17 rather than 16 just to prove that we can. Because again, on a lot of systems, we will be limited to either a 16-bit boundary or even a full 32-bit boundary, whereas not on the PowerPC, we can store to an odd boundary there. The other thing that's important is we've got store byte, store half, and store word. No mention of 0 or algebraic, and the reason for that is it simply doesn't matter when we're storing a register. If we're storing only 16 bits, it doesn't matter whether those 16 bits are signed or unsigned because they're going in memory in the same way anyway. It's when we load them back, what we do with the extra bits that haven't been loaded in. Do we fill them with zeros or do we fill them with the top bit of the value that was loaded? And so there's our load commands and there's our store commands. Now, the final thing that I think it's important to say about the PowerPC at this point, and this is true of a lot of the RISC systems and a lot of the modern processors that are coming out, and they are what is referred to as a load and store system. Now, what this means is that basically you will typically have to do things in 3 separate stages when you want to work with values. You will load the values from memory into your registers. You will perform any kind of operations, addition, subtraction, logical operations on those values in the registers, and then you will store those registers back to memory. So you will load and you will store as 2 separate things, and you have to do both to work on values in memory. Now, a more advanced processor like the 68000 doesn't necessarily need to do that. It can actually take a value from a memory address, change it, and then store it back to another memory address in a single command without any use of registers in between. And that's why it's not a RISC system, it's a CISC system, and that wouldn't be referred to as a load and store architecture because it doesn't have to do the load and store to do its calculations. It can actually do it all in one go. So it's just something important to point out about the PowerPC, and you might find if you're familiar with a system like the 8086 derivatives where there is a far more advanced range of addressing modes, you might find you're having to use a lot more commands on the PowerPC to do a simple job. You shouldn't be too concerned about that though, because the important thing about these RISC systems is they're actually a lot faster because they are reduced in that way. They are actually more efficient. So even though you're using more commands, it doesn't really matter. Okay, so there's the second set of our commands that we're looking at today. Now what we're going to do is look at some far more advanced commands. These are a bit sort of unusual, you probably won't need them, but they're worth mentioning, and this is to do with that whole little endian thing. Now we've got some weird commands that are byte reversed here. So what we've done here is we've got our sample data here, and we are going to load the word in, but then we're going to load the word in byte reversed. So LWBR here is byte reversed. And what this does is it actually loads in the bytes in reverse endian mode. So here we loaded in the value FEDCBA98, and that was done by LWZ. But then what we're going to do is use LWBRX. Now we have to use the X mode here, which will use a register offset, but we're actually using the R0 register, which is hardwired as a 0 in this case. So it doesn't actually matter that we're having to use the X. We've loaded the R0 with an 8 here just to prove that it is hardwired 0. But anyway, when we load in to R4 here, you will see that instead of FEDCBA98, we've actually loaded in 98BCDCFE, and this has been loaded in little endian mode. The important thing is this is the reverse of the mode that the processor is set in. So there we've loaded in a 32-bit value. We can also load in a 16-bit value, loading in a half here. So again, we have loaded in those bits, the 16 bits there in reverse order. But the top bit is still 1. The denibble there still has a top bit of 1, so the extra bits have been filled in with 1s there. So those are the loading commands. We also have store commands that we can use. We're not going to try those out though. Now, we do have some even more elaborate commands here. These are very specialist and not something I've really come across in before, but what we can do is we can actually load in an entire sequence of bytes in one go into multiple registers. So what we're going to do is we're going to use the LSWI command here, which is load string word immediate. Now, what we're going to do is we're going to basically specify a start register of R3 here. We're going to specify a memory address that we're going to use for our source in R8, and we're going to specify a number of bytes, in this case 6. Now what we're going to do then is basically load in 6 bytes into R3, and because we've loaded 6 bytes and each register can only take 4, it forces us to use R4 as well. So we've loaded in DCBA9812 into R3, and because we've loaded in only half of a register because of 6 bytes rather than 8, R4 contains the values 7, 8 and 1, 1. Now this seems a little bit odd to me because you can see DCBA98 and 1, 2 there have been loaded into R3 there, but R4 has loaded 7, 8, 1, 1, and it's like, well, where has 3, 4, 5, 6 gone? And it's because we haven't loaded in a full 32-bit value into R4 there. So a little bit strange there. Now, why would you want to do this? Well, you might want to do this kind of thing if you're loading it in, if you're backing up and restoring registers for some reason, or also if you're wanting to work with a large amount of data in one go. Maybe you're transferring bitmap data to your screen, you want to load in as much of it as you can, so you load in multiple registers in one go and in one single command. So it's definitely useful to have these options. As well as load commands, we also have store commands. We've got STSWI here. This is store string word immediate. I've got a typo there again, a copy paste error there, I apologize. So that's a store string word immediate here. And so when we do this, we're basically storing to an offset of 16 here again, just so we can see what's happened. Now in this case, this does actually work a lot more logically. DCB898121178, and you can see here we've stored all 32 bits from R3 and the low 16 bits from R4, and they've gone into the memory addresses that we would probably expect. So it's just that that load command basically missed the bits that weren't loaded there, the 3, 4, 5, 6. So a little bit strange there. But that's how those commands work. And they're ones you may never need anyway, but it's worth mentioning them because they are so capable. Okay, so that's all we're going to do covering loading and storing. We're going to see lots of loading and storing as we go along. But what we need to now do is we need to actually discuss how the stack actually works, because the stack is essential to things like subroutines, as well as just working with registers when we've run out of registers and we need to use them for other jobs. Now, what does the stack actually do? Well, the stack is a temporary store for values, and it's kind of like an in tray is the way you should think about it. If you imagine your in tray and maybe you've got people giving you work to do throughout the day and you're getting more work than you can do. So you've got your in tray and it's empty at the start of the day, and someone gives you a job to do, but you're already doing another job. So you put the job in the in tray, and then someone gives you a second job to do and you put that in the in tray as well. Now, when you finish the job you're currently working on, you'll start taking them out of the in tray, but you'll always take the one off the top. And so the last job that came in will be the first one you take out and work on. Then once that's gone, you will take another job out, and that will be the first job that went in, but is now the second one that's remaining in the in tray. And that's how the stack works on the PowerPC and most other systems. It's known as a LIFO stack, a last in, first out stack. Now, what we're going to do here is we've got an example routine called monitor stack, and this will show us what's going on the stack. And so let's run it and let's see what's going on. Okay, so what we're going to do is we're going to load the immediate 1, 2, 3, 4 into R3, and then we're going to store the word into the stack here. So STWU is store word and update, and so we're specifying the stack pointer as the source, which if you remember is actually register R1. It's the same thing, but SP is far clearer. And we're specifying an offset of -4, and so what this does is it subtracts 4 from the stack pointer, and because we've specified update, the stack pointer will go down by 4 permanently, and that's important because we want that value to stay on the stack. Okay, so we've basically, this could be called a push. We've pushed the value 1, 2, 3, 4 onto the stack here. And then what we've done next is we've loaded the immediate R3 with a new value, 5, 6, 7, 8, and we've basically pushed that onto the stack as well. It's the same command again. So each time here, the stack pointer will go down and this value will be stored onto the stack. Now the stack is being dumped to the screen here. You can see the stack here. Now at the start of these commands, the stack pointer contained the value 816 FFF6C, but after we'd put two values onto the stack, it had gone down by 8 and it then contained the value 816 FFF64. That's 8 lower than 6C. And what are those 8 bytes? Well, we can see there's some random values on the stack here from the other subroutines that these debugging tools are using. But once we've pushed our values of 1, 2, 3, 4 and 5, 6, 7, 8 onto the stack as 32-bit values, you can see 0, 0, 1, 2, 3, 4 at the top of the stack. That was the first value we pushed on, and then 5, 6, 7, 8 is the second value we pushed on, and because it's a last in first out stack, 5, 6, 7, 8 will be the first value we remove from the stack when we read back. Now pushing onto the stack is STWU with a negative value, but to read back, to pop off the stack, we actually need to use two commands. So we need to use load word, and so we're loading R4 from the stack here with an offset of 0, and then we're adding 4 to the stack pointer to reset the stack pointer. We can't use a value of 4 here, that won't work because that would update the stack pointer before the load, and we need to update the stack pointer after the load. So that's why we're using two commands here. But here we're loading R4 from the stack, and then we're loading R5 in the second command from the stack. And because it's a last in first out stack, R4 will contain the last in value of 5, 6, 7, 8, and you can see R4 contains the value of 5, 6, 7, 8, and R5 contains the first value we pushed onto the stack, 1, 2, 3, 4. Now there's a couple of points I'm making here. In a lot of times in our code we might push onto the stack the value R3 and then restore the value R3 later on if we needed R3 to do a different job in between. But in this case we've actually popped the values back into different registers that we pushed on, and that's to make the point that it doesn't really the stack doesn't care what we push on or when we take it off again. The stack really is just doing what it's told. Now what I tend to do is I tend to tab indent when I'm using the stack so that I can clearly see what's going on, and so that I can make sure what value I'm getting back, and also make sure that I'm popping as much off the stack as I pushed on the stack, because if you don't, you will find you could have very bad problems. Your values may be becoming corrupt, and you may even be getting crashes in some cases, because if your subroutines are being called and they are backing up the return address onto the stack, and then you push more on the stack than you pop off before returning, when you pop that return address off the stack, you will get a completely different value to the correct return address. So you may want to tab indent your stack commands to make sure that you're actually getting the values back that you think you are. Okay, now in that case we've just pushed and popped a single 32-bit value onto the stack there, but we can actually push and pop multiple values in one go, and this is going to be useful if we've got a subroutine and we want to back up all our registers in one go. Now this actually, when we use this command, we will actually specify a single register, in this case R29, and actually all of the consecutive registers from the register we specify, so 29, 30 and 31 in this case, will be backed up on the stack. Now if we'd used R3, we would be backing up nearly 30 registers, and so that would put an awful lot of stuff onto the stack. So I didn't feel that would be very clear for actually seeing what was going on in this case. So okay, so here we've basically run these commands. We've used the store multiple words R29, and we've basically allocated enough space for 3 registers here, because 29, 30 and 31, each of these is a 4-byte register, so we've specified -4 times 3 as an offset to add to the stack pointer before using this command. And then what we've done basically is we've stored the values, you can see them here, 33, 44 and 55 as 32-bit values there have been stored onto the stack here, and then we've restored them with load multiple words here, and they have been loaded off the stack. And you can see once we get to the end here that the stack is those values have basically been cleared off the stack, although that's not a function of the stack itself. My monitoring routines are using the stack as part of their own code, and so that has caused those values to be removed there. Now, as I say, these are all commands you don't necessarily need. You could store values onto the stack using individual commands in this kind of way. But if you want to back up all of the registers in one go, that is going to be a command that's definitely worth you considering. So there we go. Now, in those cases, we've used the stack for backing up and restoring general registers, and that is certainly something we're going to want to do. But there's a very important thing that the stack is going to be needed for, and that is subroutines. Now here we've got a subtest command here. Now the problem is going to be that if we call our subtest using branch and link here, this puts the return address in the link register LR, and our return command is BLR, which will jump back to the address in that link register. However, what happens if our subroutine needs to call another subroutine, a nested subroutine? Now in this case, we're going to call the subroutine that I created called monitor stack, which shows the contents of the stack. But this BL command will change the link register so that the link register will no longer be correct for this link branch and link command. So we need to back up our link register somewhere so that it is still present for when we do our branch and link BLR command here, which is our return. So what do we do with the LR register? Well, one thing is we could just store it in another register, but that gets quite confusing because if we're nesting lots and lots of subroutines, we may not know what registers are going to still be intact when we get back to the original return. And so the simplest thing to do is to simply store that onto the stack. So we may want to store our link register on the stack and restore it. What we're also going to do here is we're going to store our condition register onto the stack, because that's another thing subroutines may change, and we may want to make sure that's the same when we return. We can't unfortunately push these onto the stack directly. We have to transfer them to another register, and this is really the time when is probably the only time you actually want to use R0, to be honest. As I've said before, R0 is a hardwired 0 in some commands, and it can get quite confusing when it's going to work normally and when it's not. So one time that the R0 is often appropriate is for this kind of job at the start and end of a subroutine. So what we're doing here is we're storing R0 onto the stack because we don't want to break R0, and here we're restoring R0 from the stack. But then once we've backed R0 up, what we're doing is we're moving the condition register to R0, and then we're storing R0 onto the stack here. We're then moving from the link register into R0, and again we're storing R0 onto the stack. So this pair of commands is effectively pushing this condition register onto the stack, and this pair of commands is effectively pushing the link register onto the stack. We then run our subroutine, and then we're going to undo what we just did. So what we're doing here is we're loading R0 from the stack, updating the stack pointer to effectively free up the space that R0 contained. We're then moving R0 back to the link register because that was the last register we pushed onto the stack, so it's the first one we pop off the stack because it's a last in first out stack. We're then doing the same again, loading R0, updating the stack pointer, and we're going to move that into the condition registers. Now the condition register command is a little bit odd. Here we just specified move to the link register, but here we have to specify a bit mask. And so if we want to update the entire condition register, we basically specify a bit mask of 255 OXFF. FF is 255 in hexadecimal there. So that updates the entire condition register from the value R0 that we popped off the stack. And then finally, because we've been messing with R0 but we want it to be intact, we're loading R0 off the stack here. And again, we're updating the stack pointer so that when this returns, the stack pointer is exactly the same as it was at the start of this. And so these three sets of commands here and these three sets of commands here are a good sort of template for the start and the end of a subroutine. They preserve R0 and then they use R0 to back up the condition codes and the link register. And as I say, backing up the link register is going to be something that you're going to want to do in a lot of your subroutines if you are calling nested subroutines within those subroutines. So it's a good thing to form a habit of. Now, one thing you can do depending on your assembler is you can create macros to do this kind of thing for you. I do tend to use macros quite a lot. But to make it clear for today's example, I'm not going to use macros. We're just showing the dirty work of all of these commands. Now you will actually see that what I've got here in my basic macros is I've got a pop all and a push all. And what these are basically doing is they are firstly putting R0 onto the stack, then the condition codes, and then the link register, and then they're actually backing up absolutely all of the other registers in one massive chunk onto the stack, and this is actually restoring them all off the stack. A lot of transfers there, but these are a very good, safe thing to do at the start and end of your subroutines, and so you will see it push all and pop all in a lot of my subroutines, specifically the monitor subroutines and things, where the whole purpose of my test monitor routines is that they actually don't change anything and just show the contents of all the registers to the screen and then return and let the code continue as it did. That's essential to the testing in these tutorials, and so I use those push all and pop all an awful lot in my tutorials. Anyway, quite a long lesson here, I apologise, but we've got a lot of content done. As I always say, go to my website, download today's example, the build scripts, and try it yourself and confirm what I said was really correct, and have a play with it and see if you can break it, or see if you can understand it or make it do other things. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.